Okay, so just once again, Bob measures this distance between A and B. Delta x is equal to 100 times 100 ticks times the velocity times the time interval as measured in his reference frame, which is time dilated. So we plug in the time dilated time interval. Okay, let me just very quickly go back to remind you. Delta x is the distance between A and B, where Anna starts her counting her 100 ticks and ends counting her 100 ticks. Okay. Now, what does Anna measure? Well, she measures just the velocity. Okay, times 100 ticks times delta t prime. Her the clock is in her reference frame, so there's no time dilation, so it's just that. And so when you compare these two expressions, delta x and delta x prime, what you find is that delta x prime is equal to delta x over gamma, where again gamma is equal to 1 over square root of 1 minus beta squared. Okay, so now there you go. That's basically time dilation. I mean length contraction. The distance between A and B as measured by Anna is smaller than that measured by Bob by a factor gamma. It's important to, when you compare these two expressions, to realize that in order for it to work out this way, Anna and Bob must, in addition to agreeing on the number of ticks on the clock, so the number of events that passed, they also must agree on the relative velocity. And that makes sense, right? Because it's a completely symmetric situation. Anna sees Bob moving at the same velocity v to the left as Bob sees Anna moving at velocity v to the right. Okay, and if it wasn't symmetric, if one of them saw the other one moving at a different velocity, say higher velocity, who would it be? You can't know. So it's a completely symmetric situation. So that's important as well. Let's define the proper length, L naught, to be the length of an object in a frame in which the object is at rest. We've said that before, but I know we have a nice clean definition for it. In this case, L naught is equal to delta x, the length measured in Bob's frame. So given this definition, we have a general expression for length contraction, which is L is equal to L naught divided by gamma, where, and in words, the length L of a moving object is shorter by a factor gamma than its length L naught in the frame in which it is at rest. Okay, so again, this is a general result, even though we derived it in a particular using a particular scenario. It is a general result that applies in any case you have an object moving through another reference frame. Okay, now we considered length contraction only along the direction of motion, only along the coordinate axis that was along the direction of motion, direction of relative motion. So it's a reasonable question to ask is, do we have length contraction in a direction perpendicular to that direction of motion? Okay, and the answer is no. And to see this, we basically consider a simple situation where we have Anna and Bob. They're both holding pipes of equal diameters, d, okay, and they're running towards each other with some relative velocity v. Okay, so Anna has her pipe, Bob has his pipe. They both have the same diameters, and they're running towards each other with relative velocity v.